Welcome. We now start a discussion that will extend into several discussions, several lectures. In the context of mathematical epidemiology, the description of epidemics with mathematical models, and the interplay between some of the basic and general concepts we learn from game theory when applied to immunizations or vaccinations. This is a very important topic in the context of epidemiology, and we will revisit this topic. Most of what we're about to discuss is in reference to this paper by Bach and Ern, published in 2004. But you have to keep in mind that here, what is at um, uh, what is at stake is that individuals must make decisions. These decisions typically require that they factor in knowledge they have about these immunizations. Some of these immunizations, some of these vaccinations confer a very high level of protection and immunity against an infection, but some of them have side effects, and some individuals are then faced with making the decision on the trade-offs as to whether they're better off being protected or if they are worse off dealing with the aftermath by having this immunization. The other thing to keep in mind is that once an individual is immunized, that person is protecting himself or herself, but it's also offering some protection to others that are in vicinity concerning the mode of transmission. And this relates to something that in epidemiology is called herd immunity. It's like the immunity of the group. So a lot of interesting concepts, and we are just about to get started with some of the basic elements of vaccination and game theory. So one of the most basic models of epidemics we know is this model we have here, the equations. We have the equations of the model that's typically called susceptible, infected, and recover, with the initials SIR. This model, as you can see, has already been rescaled. Therefore, the state variables are adding up to 1. And as we have previously discussed, the SIR model can be rescaled into a system that has different time units, and it gives you a model that has now no dimensions, right? So we can reduce the number of equations into 2 equations, and also we can have a non-dimensional system by choosing a new time unit appropriately. We have already worked the details of these calculations, and we're simply kind of refreshing our memory here. So an illustration that dates back to the original model, the SIR model here in proportions. A box illustration looks like this, where we know that in the first box we have the susceptibles. There are some transitions from the susceptible class into the infected class, and the infected individuals may be removed into a class that we denote here by R. The rates of transition, these equations all have a rate of departure, here denoted with mu, so we know that there are mu departures from S, there are mu departures from I, and there's the same number of departures from the last group. The key transition for infection here is parameterized by the transmission or infection parameter, and that allows the rate of new infections to be beta S times I, and then there is a recovery rate of gamma. Okay, everything is good there. The one thing to notice is that we have this model assumes that there is a fraction of individuals that are confirmed permanent immunity, and that fraction, that proportion of individuals never first we assume that all newborns are born susceptible, but this model takes into account that a fraction of those newborns are immunized, and so that fraction is a fraction p, and we have p mu going in directly into the class or compartment with permanent immunity, and there is only a fraction 1 minus p that are assumed to be susceptible. Okay, so that's precisely this fraction here. Now, the model that has no dimensions has a new time unit, right? So the state variables for this model here that has two equations, those state variables are s, but we are here writing s really as a function of tau, where tau is the new time unit, and then I is also assumed to be a function of tau, not t as we had in the original equations, but tau. The other thing we want to notice is that um, in this for this new model, the box representation or diagram representation would look like this. We have a compartment of susceptibles still. Some of them may be transitioning into an infected state, infected and infectious. The rate of transition now for this new model, where these are some of the mathematical um, transformations or change of variables we had to do. Well, they're not variables, they're parameters, but now there are new parameters to write these equations. So that the transmission now is something that is expressed here in terms of a parameter R0 times 1 plus F, okay, and that still multiplies S times I. That denotes the transitions going from S into I. And there are arrivals into the population. Those arrivals are happening here at a rate f times 1 minus p. You want to remember that p here is the proportion of individuals that are receiving immunization. Okay, and then there are departures out of this compartment. Now the departures are f times s, and then f, excuse me, in the case of the compartment I, the departure is 1 plus f times I, right? So you can verify the expressions I'm writing on the box compartment relative to the equations. And so to keep in mind, what are the names of these new parameters? R0 is known as the basic reproductive numbers. The basic reproductive number, which in terms of the original parameters is given as beta divided by gamma plus mu. F, this new parameter f, is a fraction. Is the fraction that divides the um, the infectious period 1 over gamma by the mean life expectancy, which is 1 over mu. So f really is mu over gamma, but you can interpret that as this expression 1 over gamma divided by 1 over mu. And then we have that parameter p, which denotes in this case, this is what we would call the vaccine or the vaccination uptake level. So there, we're going to define a critical coverage or a critical level of vaccination, which we denote as P sub C, and we define this in terms of one of the parameters of the model, which is the basic reproductive number. So we say we're going to let this critical level, critical coverage be 0 if R0 is less than or equal to 1, and we let that be if R0 is bigger than 1. Then this quantity is defined as 1 minus the reciprocal of R naught, 1 over R naught. So now we're going to see how this critical level of coverage or vaccination coverage plays a role on the dynamics of this model. Specifically, if the vaccination coverage P is greater, if it exceeds the critical level, then we have this result that says that the equilibrium point that has stability is the equilibrium point that we call the disease-free equilibrium. Okay, so an illustration, plugging in some values for the parameters, an illustration appears here. So we can see in blue, that this curve here is S of tau, while in red we have the curve I of I as a function of tau. So clearly, in this illustration here, the infectives are going to zero as time tau progresses, and susceptibles are going to a stable equilibrium, which is given by 1 minus p sub c, which is the critical coverage. So just for the sake of illustration, here are the values. You can use these values to code this app into R using the function L soda, and you can verify these two curves. The other scenario is when the vaccination coverage is above the critical, excuse me, when it's below, when it is actually less than P sub C. In such case, the equilibrium we typically call endemic equilibrium, which is in this case given in terms of the parameters of the mole and the value of P sub C, then when P is less than P sub C, this equilibrium point is stable. And here we have some illustrations of this. This implies that S converges to this value 1 minus P sub C, and I, the number of infectives, would converge to this positive value. So it's clearly when you have here P less than if you move one of these quantities to the other side, then you have that P sub C minus P is strictly bigger than 0, which means that this quantity here is positive, right? So we have both susceptibles and infectives converging to a non-trivial positive equilibrium level. So here we display the parameter values and the initial conditions that are used to obtain this numerical solution. Again, you can easily code this with L soda and R, and we have basically covered the basics here of the basic SIR model, the dimensionless form of this model, and we have defined one of the key parameters in this new formulation is the vaccination coverage, P, together with a critical level of vaccination, and we can see how the dynamic behavior of the model depends on this new parameter P sub C. Therefore, we have illustrated both stability of the famous disease-free equilibrium and stability of the endemic equilibrium, both in terms of this critical coverage.